Hello everyone, welcome to Practically. We bring learning alive. Today I am going to demystify the concept, or I would say exception, in electron gain enthalpy. Previously we have demystified the exception in ionization enthalpy. So this is our concept simplified series where we have already covered the ionization enthalpy. Previously we have covered this, okay, and in today's lecture I am going to demystify some exceptions or some irregularities in electron gain enthalpy, and that will be followed by acidity basicity order, the abnormality in those properties, then stability of carbon's compound, and then organic reactions. Okay, that will be followed after this. But in today's session I am going to demystify the exception in electron gain enthalpy. So first of all, what is the definition of it? What is mean by electron gain enthalpy? Do you see here? Just a sec. Do you see here? This is the electron, and this is what? This is your nucleus. This is where your nucleus is, right? That is your nucleus. Now these are what? These are your shells. These are your shells, right? And your electron is being added into this. So basically the amount of energy evolved or absorbed when the electron is getting added, the amount of energy evolved or absorbed when electron is getting added into species, into bracket, atom, molecule or ion, is called as electron gain enthalpy. As the name suggests, electron gain enthalpy, it is just opposite to ionization enthalpy. You can literally say that ionization enthalpy is equal to negative electron gain enthalpy. You can basically say this. So that means for a given atom, if it is losing electron, and while losing electron, obviously when you're plucking out the electron, the process is always endothermic. So when you're plucking out the electron from an atom, molecule or ion, suppose it actually involves the absorption of energy around 100 kilojoule per mole. Then when you add the same electron into it, what happens is that 100 kilojoule per mole energy gets evolved. Okay, now as per the normal thing, or as per the regular things in chemistry, we know that whenever you are breaking something, it always associated with absorption of energy. And whenever something is forming in chemistry, it is always associated with release of energy. Okay, but so that's a two regular thing. Now it is not necessary that it will happen always. Okay, what I said just now, it's a regular trend in chemistry. But as you all know, chemistry is not a chemistry without an exception. Okay, and in electron gain enthalpy also we are going to see the same thing. You can see this diagram where electron is getting added here. What you are getting here, this energy is getting evolved. This is nothing but what? This is your evolved energy. This is your evolved energy. That is why I put it like that. Okay, so that's what the definition. Chalo. Now let's see what's the trend. What's the trend in ionization enthalpy? See, basically electrons are getting added. Now whenever the electrons are getting added, it is always about the nuclear charge and size. Okay, nuclear charge and size would definitely have an impact on the value of electron gain enthalpy of particular atom, molecule or ion. Okay, so what's the trend? So you can see the trend, electron affinity is directly proportional to effective nuclear charge. What's the meaning of that? Higher the effective nuclear charge, higher is the electron gain enthalpy. Because whenever you are adding electron into the system, what happens generally is that, see, if suppose this is your system, positive charge, these are your shells, okay, and what happened here is that the nuclear charge the nuclear charge is generally spreaded like this till here. It is spreaded till the last shell. So whenever you're adding a new electron into it, whenever you're adding new electron into the system, what happens is that electron is getting attracted strongly by the nuclear charge, which is released by a nucleus. And obviously that causes what? That causes a development. That causes a development of force of attraction, or I would say a kind of a bond. I wouldn't say a bond, but electrostatic force of attraction is developed between the nucleus and the incoming or test electron. Now obviously that means something has formed. If something has formed, it will surely release what? It will surely release some energy. And that is why electron gain enthalpy is more often than not a negative. See, it releases the energy obviously, but as per our sign convention, we give a negative sign to it because it's an exothermic process. Okay, so if I give you a general trend, ionization enthalpy is endothermic and electron gain enthalpy is exothermic. But we had seen previously that it is not necessarily like that. Ionization enthalpy is always and always positive. There are some cases where you might see it be a negative, but electron gain enthalpy could be negative, could be positive. Okay, as you will see as we progress ahead. So, as per the regular trend, electron affinity is directly proportional to effective nuclear charge. Now we know the periodic properties, right? What are the periodic properties? See, as you are moving in period, from left hand side to the right hand side, what happened is that nuclear charge increases. So as the nuclear charge increases, electron gain enthalpy would also increase. You will see that here. See, this is your hydrogen, helium. Now hydrogen has some electron gain enthalpy, no doubt about it. But as soon as it go to the helium, electron gain enthalpy suddenly decreases. Why? Because helium is a noble gas. It doesn't want electrons to get added to it, nor it wants electrons to lose. Okay. So then again it went to lithium. Again you can see it's a positive value, right? From lithium again it decreased to beryllium. Beryllium is almost having 0 electron gain enthalpy. Then it kept on increasing till carbon. Then it again decreases in nitrogen. Then from nitrogen it kept on increasing through the oxygen till fluorine. So basically, if you are talking about hydrogen, helium, lithium, so basically you are talking about the first two groups. If you are talking about, not groups actually, periods, not periods. If you are talking about first two periods, the electron gain enthalpy is highest for the fluorine. Why? Because fluorine is having highest nuclear charge. Fluorine is having highest nuclear charge. But did you notice some exceptions here? What were the exceptions? See, helium is having higher nuclear charge than hydrogen. Still helium's electron gain enthalpy was almost 0, or I would say it was positive. It was positive. Similarly for beryllium it was almost 0. Then it kept on increasing till carbon. Then suddenly it dropped to nitrogen. So basically there are 3 exceptions here. This one, second and third one. So you see there are 3 exceptions just in the second period. Okay. Chalo, let's move ahead with this now. Now, what's the second trend? Electron gain enthalpy is not only decided by your nuclear charge, but is also decided by the size. And what's the size? See, electron affinity is inversely proportional. It is inversely proportional to size of atom. That means what? In the previous slide we saw, basically we were talking about a period in that. Okay, in periodic table you have periods as well as groups. Here I am talking about groups. You can see electron affinity is inversely proportional to size of atom. That means as you move from here to here, electron affinity would increase. That means if you go down the group, for example, fluorine, bromine, iodine, or astatine. Or you can have any other example. For example, you can have hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, like that. So as you go down the group, the value of electron gain enthalpy decreases. Why? Because as you go down the group, the size of an atom increases. As the size increases, the value of electron gain enthalpy decreases because they are inversely proportional. Okay. So this is again the regular trend, but again you would see or you would find the exception to this also. Okay. Let's move ahead. Third, electronic configuration. Third thing which decides the value of electron affinity is electronic configuration. What is the regular trend here? Say this is a half filled p orbital. This is a fully filled p orbital. If you try to add an electron here, if you try to make an attempt of increasing electron here, it would not add an electron. It will be reluctant to add the electron. And even if you add the electron, what will happen is that its electron affinity would be positive. You would see its value of its electron affinity would be positive because you are forcing it. Half filled is what? Half filled has extra stability. As we all know, half filled orbital and full filled orbital, both of them has extra stability. So they are already stable, but you are forcing it. You are forcing them to have an electron. Okay, and that is not right. That is something which is abnormal or against their true nature, and that is why they would do so, but they would not show you a regular trend of releasing the energy. In fact, they will absorb the energy and then only it will do. It is just like, it is just like giving a bribery to officers. If officers are doing their regular work, if you are going to them and if you hand over papers to them, they have to do what? They have to check it, they have to sign it, and they have to forward it to their higher officials. But generally we had seen in India, they don't do these things. So what do? Is that they charge for the bribe. And a table ke andar se jaise hum bolte hain. So that's like they do, right? So that means you are giving something to them so that they would ease your work. Okay, just like that here. This nitrogen would not accept electron that easily. It would only accept the electron if it releases some amount of energy. Okay, so that is why this is endothermic of nitrogen. So I would say it releases very less energy. Same thing is with the half filled orbital. Okay, now, so do you observe now, when you went from carbon to nitrogen, electron affinity was actually decreased. So why was it decreased? Because if you see the electronic configuration of carbon, it was 1s2, 2s2, 2p2. This is the electronic configuration of carbon, right? So it has 2 electrons. And if I write about nitrogen, it would be 1s2, 2s2 and 2p3. So you can see here nitrogen is already having half filled p orbital. Nitrogen is already having half filled p orbital. That means it has already achieved the stability. It doesn't want to go away from that stability, and that is why it will not add on that extra electron. However, carbon, you can see carbon has got what? Carbon has got this 2 electron. If you add one more electron here, your carbon now would be half filled. Your carbon would be half filled, right? So that means carbon knows that if the electron is getting added to me, I will become half filled, and that is why it releases the extra energy in the form of obviously electron gain enthalpy. It releases the extra energy. That was the reason carbon having abnormally high electron gain enthalpy than the nitrogen. So basically these are not the exception. There is some reason to it, and that is what, and that is why I'm here to demystify that. Okay, chalo, next slide. So this was the electronic configuration of carbon, as I was saying. 1s2, 2s2, 2p. This is basically what? This is basically your carbon. So if you add one more electron here, it will become half filled, and that is why it accepts that electron gracefully and releases huge amount of energy. Okay, because it knows that it's going to be stable. It is just like that. If I ask you to come downwards, or if I ask you to go somewhere for some work, if your mother asks you for some work to go to the market, okay, you will be like, oh mom, I don't want to come and all that. But suddenly your father comes to the evening and he says, hey, tomorrow we are going for AdLabs Imagica, we are going for some vacation. You would be so energetic, right? Because you know you are going to get fun and all that. So it is just like that. Carbon knows that it is going to get stable when it accepts that electron. That is why it releases a huge amount of energy. And that is why it doesn't need, you don't need to push the carbon for the acceptance of electron. Whereas for the nitrogen, it is already at a stable state. It is very, very stable. That is why it is already enjoying its state. So if you want to move it from its stable state, you need to give him bribery. And that bribery means what? Nitrogen would release less amount of energy, or I would rather say its electron gain enthalpy would be endothermic. Okay, just like that. Sure, moving ahead. Oh, sorry. Now we're gonna see here that, see, moving in periodic table. So when you move in the periodic table, what happens? See, this is what, here you are moving in periodic table from left to right. Okay, here you are moving in periodic table from left to right. Here you are moving in periodic table from top to the bottom. Basically this is in groups, this is in periods. Periods, groups. Okay, so electron affinity in periods. Now what happens? When you are moving in periodic table from left to right, the value of your electron gain enthalpy increases. Why? Because the nuclear charge is increasing, right? We had already seen that. And when you are talking about periods, or I would rather say when you are going from top to bottom in groups, the value of your electron gain enthalpy also decreases. Why? Because the nuclear charge is becoming less and less concentrated. See, when the nuclear charge in a small area, it is very highly concentrated. So even if you add an electron to it, that extra, or I would say concentrated nuclear charge would get balanced by that added extra electron. Okay, but when the size is increasing, this density of this nuclear charge decreases, and that is why it becomes reluctant to add an extra electron, and that is why electron gain enthalpy decreases. Okay, that is what the trend is, but we are here to demystify an exception. Okay, now look at this. Now here we are basically talking about what? We are basically talking about group. Which group? Now you need to understand that hydrogen is not actually the part of this group, but for the sake of simplicity, I take into this group only. So hydrogen, lithium, sodium, potassium, rubidium, cesium. These are what? These are all, if you don't consider hydrogen here, these all are S block. I would rather call them as alkali metals, isn't it? So they are alkali metal. So as you are going down the group, you can see the value is getting decreased. See, it has decreased, right? Why it's decreasing? As I told you, the nuclear charge, or I would rather say density of a nuclear charge, density of nuclear charge is getting decreased. So since it is getting decreased, therefore your atom is not ready to accept an electron. Okay, so it is pretty much regular here, but now let's look at this in the period. See, for lithium it's 59.6, we just saw. right? Electronic configuration of lithium is what? Now I would just write 1s2, 2s1. Okay, 1s2 I would not write again because it will be carried forward in each and every atom thereafter. Okay, so I will keep it like that. I only write 2s1 or 2p, whatever. So when you went to the beryllium, what happened is 2s2. Now lithium, 2s2 is what? 2s2 is this. Fully filled shell. Fully filled shell. Now lithium knows that when the electrons are getting added into it, it will achieve the fully filled subshell. That is why it is ready to accept the electron, and therefore it releases a huge amount of energy upon an addition of an electron. However, for beryllium, this value seems to be 0. It is actually not 0. Beryllium has some value, but again, it is what? It's an endoergic value. It's a endoergic. That means it's a very highly endothermic. Okay, and many of those have not been studied, but people knows that it will release huge amount of energy. So for a time being, let's consider it to be 0. Okay, now you went to the boron. What is boron? Boron is 2s2, 2p1. Now the effect of increasing nuclear charge. Now the effect of increasing nuclear charge will come into play. It will come into play now. See, negative, further negative. Why further negative? Because what is the carbon's electronic configuration? 2p2. Carbon knows that it will become 2p3 upon addition of an electron, which is half filled. That is why carbon's electronic enthalpy is very high. I'm not saying highest, but very high. For the nitrogen, again it's plus 6 plus 31. Why? As I told you, it's a half filled orbital. It is already stable. It doesn't want to go away from that stability. Again, the increasing nuclear charge factor will come into play. So oxygen will have negative electron gain enthalpy, and we see fluorine is having the highest electron gain enthalpy here. Why? Because fluorine is most electronegative element in the periodic table. But if you are talking about group here, as far as this period, it is the most electronegative element, and therefore, in fact, it is smallest in size also. Because of that, its nuclear charge is very densely concentrated. That is why it can afford to add an extra electron. Okay. Now let's look at all the values here. If you see here all the values, see lithium, sodium, potassium, rubidium, cesium. Okay. Now let me point you out something here. What I want to point out here is that look at the value of aluminum boron. Do you remember, as I told you, that as you go down the group, the value of electron gain enthalpy also decreases. But look at here, when you go from boron to aluminum, it has actually increased. See, it has increased. Similarly, when you are going from carbon to silicon, that time also it's increasing. From nitrogen to phosphorus, also it's increasing. When you go from oxygen to sulfur, see, that time also it's increasing. When you go from fluorine to chlorine, that time also is increasing. See, isn't it something strange? As far as your property or your group trend is concerned, or your group trend is concerned, what was your group trend? As you go down the group, as the size increases, the value of electron gain enthalpy decreases. Now, that was true, but not in every case. So, are these an exception? The question is, are these an exception? The answer is no, they are not an exception. Why? Because, see, this boron, carbon, nitrogen, oxygen, fluorine. If you are talking about boron and aluminum, carbon and silicon, nitrogen, phosphorus, oxygen, sulfur, fluorine. In both of these two, this is group 2. These are belonging to second period. This is your third period. So basically, when you went from second to third period, if you're talking about boron, carbon, nitrogen, oxygen, fluorine, for them, their size is very, very small, right? So nuclear charge is concentrated, fine. But we are paying only attention to nuclear charge. What about the electron density? These atoms, they are already having some electrons, right? Maybe 2, 3, 4, 5, whatever. Boron is having 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, right? They're having that many electrons. So when you're adding an extra electron to them, since they are small in size, addition of an extra electron causes inter-electronic repulsion. Addition of that extra electron causes inter-electronic repulsion, and that is why they are reluctant to add an extra electron, or even if they add an extra electron, they will not release that much energy as much it was released by their family member which are present in the third period. Okay, now that's the reason why they don't have much higher values. But now the again question comes, then why do this element has a higher value than them? The reason is, see, we are right now in the P block, right? So P block are what? They are non-metals. So they are non-metals, that means they are electronegative. So since they are electronegative, they are bound to have an electronegativity. So electronegativity factor is here also. It is being played in the third period also. But the thing is that along with electronegativity, their size, the size of your aluminum, silica, phosphorus, sulfur, chlorine is obviously higher than their first member. So the larger size and considerably high electronegativity, both these factors contribute for these atoms, these elements to have a slightly, or I would say higher electron gain enthalpy than their family members. That is why chlorine is the atom which is having the highest electron gain enthalpy in the whole periodic table. Now that does not mean that chlorine is most electronegative. The most electronegative element is still fluorine, okay? But electron gain enthalpy is highest for chlorine, okay? I hope you must have been clear with all the exceptions that we have summarized today. Okay, so again the question, exceptions, okay, are they really an exception or does it have any reason, right? We just have seen what are the reasons. So in chemistry, yes, there are some exceptions surely, but it is not that no exception has a reason. Almost every exception has some reason behind it. Okay, there might be 1 or 2 exceptions here and there which do not have any reason at all, that you need to remember, but most of the time the exception would have some reason surely, and I am here to tell you or to demystify those exceptions only. Okay, see you next time in the next demystification. Bye.
Bring learning alive practically.